project students again, back to our great tea experiment. Let me just rotate this so that we can get the whole of the board in. Ooh. Yeah, there we go, that's better. So let's have a look at the next thing. I've been back in the lab and I've done a few measurements, so we've got a little bit closer to knowing what we want to do, or at least I have. Let me sketch the possibilities. So this is what I did. I took a stirrer plate, heated it up with some water in, tap water in this case, 100 milliliters of tap water to 95 degrees C with 1 tea bag. With a stirrer bar in it at the lowest possible speed, and I took out 1 milliliter to test. I actually did it twice. Once I did for 10 minutes and once I did for 30 seconds with different tea bags, so that I had a lot of liquid to do a lot of tries, but it turned out that I only needed 1. So I then extracted it by first of all adding sodium carbonate solution to it a little bit. It wasn't quite saturated, so we can go up in concentration. Then I added 2 milliliters of carbon dichloromethane, CH2, Cl2. That extracts the caffeine, and it's also heavier than water, which is handy because then it comes out the bottom and the tea stays on the top. So I did that twice to get 4 milliliters. Again, it turns out that that's not strictly necessary. We can think about that in a little bit. Put it into this container, the cuvette, which is for measuring ultraviolet visible light. Shone a light through it into a UV 2000 spectrometer, which is a little tiny box, and measured it on this computer that I'm using to make this film. So what are the results? Well, the first result is, well, hang on, let's have a look at them. That's probably the best way. So let's have a look at the spectra directly on the screen. These are the spectra. Let's have a look. The first one is the blue one, which was 30 seconds of tea. So it was steeped for 30 seconds. 1 milliliter of it was taken, and it was extracted into 4 milliliters of dichloromethane. And that is the blue one, which is very low at the start, which we expect. Then as we go further along, we get a peak, which is near the value that we would like it to be. 275, 270 is the literature value of this measurement. So we see that it goes up. We also see it goes up very low values, but we're not so interested in those. However, we get a sharp peak at going up to 0.8 on our scale. If we take 4 minutes tea, we can see that it goes up very high before this, and then the signal disappears somehow. So the measurement system shows that as naught absorbance, but really what's happening is it has had a problem with the maths because no light is coming through, so it's divided by naught and then it's got infinity. So we've ended up with a problem. So what I did then was the green curve, which was to dilute it, in this case by a factor of 10, which brings it back onto scale. So we need to dilute this tea to bring it back onto scale, which tells us that we have plenty of caffeine. So if we take a 1 milliliter sample, we can definitely measure it in the time that we've got. 0.8 is a good amount of absorbance. We can definitely measure this amount of caffeine. If we measure it for 4 minutes, we've got far too much. It's way too concentrated, but we can dilute it. Or we could take a smaller sample. Changing diagram, so if we zoom in and measure just the tea in this case, without extracting it, so this is the full tea, we can see that we get a color change, and it does the same if we have the 4 minutes tea. It has a cutoff at low wavelength, so short wavelength. It's effectively black to it, which is why the tea looks kind of reddish. It's absorbing all the blue light and absorbing less red light, so that's why tea looks red. But we can see that it very quickly saturates our detector, it breaks and goes to 0, and we probably shouldn't go anywhere near where the detector gives up. It's not the best detector, we can get better than this, but these measurements show that we can take measurements here. If we take that data, so if we take this data and we divide them by each other, so if I take the red one and divide it by the blue one, it tells me what proportion of it is it. So if we were to say measure at 600 and we measured this amount of brownness, and then we waited for 4 minutes and we measured this amount of brownness, would it make a difference if we measure, say, at 550 instead? Would we get a different value? So what I did was I divided the whole spectrum. That's obviously going to break down when we get down here and when we get up here, because this is another peak for something else that we don't know what is, and this is passing the threshold of the detector. It's going into a non-linear region, so it's not working. We can see that on our measurement here, so down at long wavelength, it gets all messy and all jaggedy. Down at short wavelength, it goes insane and then drops to 0 because it can't measure anything. So that part below 450 is irrelevant to us. The interesting part to us is that between 500 and 550, maybe up to 600, the value is fairly constant. It's not super constant, it's not the best value, and there is going to be a problem because it's not just one chemical that's coming out of the tea to make it brown, it's a whole family of chemicals, but it is flat enough in this region that we can use it to measure brownness. We just have to define somewhere along the flat bit, so somewhere between 500 and 550 is reasonably safe. We can choose as our brownness measurement. If we go further along, so this is the checking what my sodium carbonate does. So if I take my tea after 30 seconds, it has a spectrum that peaks at short wavelength because it's absorbing the blue light, as we say. But then if we add sodium carbonate to it, so I added 50 microliters of sodium carbonate to 1 milliliter, and it caused this weird peak in the purple curve to appear. Then I added another 50 microliters and it went to the green curve, so it got bigger. And then I added another 100 microliters and it went to the red curve, which is not massively different to the green one in this scale. So we can see that there's a color change on adding sodium carbonate. That is something that tells us we should probably be careful about the water, because this is the same as having hard water or not so hard water. So we should probably use distilled water for our actual measurement. This was using tap water because it was a test and we want to know what's going on, how much caffeine's coming out. So it's irrelevant. I was going to add carbonate anyway, but in the real test we want to know how does the color develop, and small changes in the amount of carbonate in there will cause a big change, particularly at the wavelength that we're looking at, somewhere around 550. It's nearly a doubling. So we need to be very careful there. So I suggest using distilled water because buffer doesn't boil very easily. If we go out to that region, or nearly that region, you can see this zoomed in. So it goes from blue without carbonate to red with a small amount of carbonate, and then the top two are with carbonate and they lie on top of each other, which is good because it means that the amount that I chose, 200 microliters, is already saturated for this chemical. But because it's a relatively sharp acid-base reaction, it probably won't change the pH much after this point. Let me close this and go back to the board. So staying on this picture, we can see that 1 milliliter from 1 tea bag, so 1% of 1 tea bag. Let's put that here, 1% of 1 tea is easily enough to be detected, and I had to dilute it by a factor of 10, so let's put another naught on here, 0.1%. Let's use a pen that works. So if we have, we have 1,000th of a t to detect, to measure. That is a data that we've found out. Oh, that looks black on there, it looks red to me. So we need 1,000th of a tea bag's worth of tea to be able to measure it. That's okay, because then we could either extract or we could use lots of different ones, but with one bag each time. We need 1 milliliter to be able to measure, or we need 1 milliliter to be able to measure the tea color. And 1 milliliter is plenty to measure the tea bagness. It's more than enough. Okay, so let's see what we've got. We've got two possibilities that we could easily do. We could take 10 tea bags. I've written tea as an old tea to tell the difference between temperature and time. So temperature is a big T. T is in old style, capital English style, is a tea bag, just so that we know what we're doing. So if we take 10 tea bags in a litre of water, we heat it up and stir it. We take 1 milliliter out each time. We need a milliliter for the measurement of the caffeine, possibly less, and we need a milliliter for the measurement of the tea color. In the best situation, because we needed only 1/10 of a milliliter to do it, we could use the same amount, because we could use 1 milliliter, put it into the spectrometer, measure the brownness, and then we can take half of that and extract the caffeine, and that would be fine. The advantage of doing that is we will never get the whole milliliter back out again, but we can get most of it back. So we could do this, and every time we take a milliliter, we use about 1,000th of the solution. So if we know how many measurements we need to make, we can work out how much that's going to affect our measurement. So if we look here, this is what we expect. Sorry, I've drawn on it twice because I said this and I forgot to record it. Here we have the type of curve that we expect. So it goes up quickly to start with and then slows down over time, and it never really finishes. That's the kind of curve you expect with extraction, an exponential curve. So this is time on the bottom. This is concentration of caffeine or brownness. Both of them should do the same, but we don't expect them to have the same time constant. So they might be a different shape. For that purpose, I measured those samples beforehand, and we see that there is definitely a difference between 30 seconds and 4 minutes. So it will be somewhere around here. Then we need to measure before 30 seconds because there was still significant caffeine in there and significant color. And after 30 seconds, we need quite a lot of measurements because it goes up to 4 minutes. So I've taken 15, 30, 45, 60 seconds, 90, 120, and 240. I think it will be difficult to get it more accurate in time than every 15 seconds because there is a practical limit to how quickly you can add things and take them away. With this method, it might be possible if we just take one tea bag and 100 milliliters and dip it in as I did in the video for the time, pull it out, then it might be possible to do that better because then we can take sharper time steps in our reaction because then I can pull it out. That's a single time step. So you can do that with an accuracy of maybe less than a second. Probably a second is practically possible. It's going to be difficult to take a second sample inside 15 seconds. That's already a challenge. So if we do this, this is good for certain reasons, because it means that we've got all of the tea bags in there, got the same temperature, got the same stirring, we're measuring the same solution, so those things are all working for us. If we do this one, we get sample, so if we make a mistake, if I make a mistake, because it turns out that I got to do all the work this year, if I make a mistake, I can make the measurement again, because I've got a whole 100 milliliters of tea to play with. But we have the problem that if there is a variation in the amount of tea in a tea bag, or the temperature, T, or the stirring, whatever we want to call that, stir, S, those things will cause our curve to have some kind of noise on it. The thing that I was worried about was that taking volume away would make a significant difference to the volume of our tea beaker. But as you can see, if we take these 7 steps, we take 1 milliliter each time, or even 10 steps, that's about 1% of the total volume. So we're only going to change the answer by 1. And I don't think we can measure the concentration of caffeine that accurately that it will be visible. Obviously, if we took 100 measurements and we've changed the concentration, the volume by 10%, then we will not be able to use it at all, because it will go weird unless we compensate for that in some way. So that's one style of measurement, and this is a second style of measurement. Let's have a look at some information on the tea bags. So in an attempt to resolve this, I weighed some tea bags, 5 tea bags, and I got different masses for all of them, and you can see the mass is not that badly off. It's off in this last digit, so it's in the single percentage range, but the difference between 0.92 and 0.85 is quite a lot. It's 0.07, so we take, so it's not super large, but it's also getting into the range of 8%. We can have a look to see whether that's a big problem, because obviously I weighed the bag, so there's also the clip and the paper and the bit of string and stuff on there. So let's see what happens if we empty the tea out. So these are the weights that I measured of just the bag, of this one here, the lightest one, and this one here, the heaviest one, and you can see they're not much different, 0.312, so it's in the 3rd decimal place behind the comma. It's not a huge difference, which means that the tea is quite different. The mass of the tea is quite different in the different bags. That's bad news. The good news is that because the bag and the clip and the bit of string weigh pretty much the same, then we could weigh the different bags beforehand and choose a group that have similar masses to cut down the variation. So if I want 10 tea bags, I can choose 10. It's a box of 50. I have used some, but it's a box of 50. So there's quite a lot extra that we can use for grouping. It means that if we choose a different temperature, we might have a different group of masses that we need. It also means that if we use groups of 10, we can weigh them together to select a group of 10 that is similar. Because again, the masses of the bags are very similar, so it's the tea that varies. So if we take 10 that together weigh 10 times this one, so 18 grams, if we take 10 that weigh 18.5 grams, we will know that if we take another 10 that also weigh 18.5 grams, we've got almost identical amounts of tea, and the variation in the bags will be unlikely to hit us there because they will even out. Although it's dangerous to hope that. However, it is quite a small variation, so it's not too bad. So we still have our 2 possibilities still alive, and we still have to think about, is the problem of getting the temperature right and the problem of getting the mixing and the extraction point right and sucking it up right, is that worse than the problem of having, well, hang on, let's write down the possibilities because I seem to have mixed them up. Let's do that on the board. So I'll rub this off and start again. So here I am back with my table. So if we take 10 tea bags in a litre, we only have one extract. So if we mess it up, if I mess it up, so every time point we have 1 milliliter, there's only one chance to get our measurement. If I mess it up, we've lost. Have to do it again. If we have 1 tea, we get up to 99 goes at it, which even I cannot manage to mess up. The temperature in our measurement is constant throughout the mixture because it's stirring, so the temperature is not going to vary through the container, and it's comparatively big, so its temperature is going to be much more constant, and the stirring is going to be the same for all of the different samples because it's in the same container. They're all coming out of the same batch, so there will be no problems there. Here the stirring and the temperature will be new each time. The stirring will be difficult to keep constant. The temperature will be difficult to keep constant because they are new every time we set it up. The temperature is new and the stirring rate is new, and that could be a problem. So we've got 10 measurements at different temperatures. That would be bad. So obviously a practical issue that this is way more difficult to set up than this one because of the temperature. The time on this one is challenging because it's challenging to extract the correct volume in a short time at exactly that time. This one, the time is more realistic to a tea bag, because what are you going to do practically if you're going to actually do this to regulate your caffeine intake? You would take the tea bag out after a given time, but obviously we're not going to squeeze it because that is another layer of complexity, and we have trouble with the amount that dribbles out because practically as it comes out, some more concentrated tea will fall in. We will cause some forced mixing, which will not be the same as this case. In this case, we've got the variations in the amount of tea in the bags we can compensate for by choosing clusters of bags that have the same total mass. And here we have variations in them inside the run and also between different runs, so that could be a problem. In this case, you can't see it, but there's a volume change during measurement of around 2%, which would cause us a 2% error in our last measurement. At the beginning, it won't be so bad. At the end, we will get a 2% error in our measurement. In the other method, the volume change is an error. So we got an error of how much of the water evaporates during the measurement, but that's the same, and how much can we get an exact volume into the container in the first place. Luckily we have values for that. If we use a good measurement system, so a pipette or a volumetric flask to do our measurement with, we can get a measurement of around plus or minus 0.01 milliliter, and that means that we can get well below 1%. So that is not a problem here. The problem is how much evaporates, because obviously as time goes on, more and more will evaporate. And if we take different times to get to the correct temperature, we can't tell how much it is. So we will have to come up with a mechanism here to cut down these errors a little bit of the temperature that we're starting at and of the volume. So ideally, we would measure the volume hot if we're going to do these, or ideally we would keep all of our liquid at a constant temperature so that we don't have a change over time, because we've got 5 minutes and it will cool down. The larger the volume, the less it cools down, but it will be better if it didn't cool down as much, and if we could keep a large volume at the correct volume, at the correct temperature, for the time that it takes me to do all of these measurements, which is going to be a long time. So think about those. We've got to make a strategy of how we're going to do this experiment. It now looks like it is possible. It's very likely that people have done it. I found a website of a tea company who claim exactly the thing that I said, so it's not just me making it up. I thought it might have been, because, hey, it's something my mother said at some point, but it turns out that a tea company do say you can regulate the amount of caffeine that you ingest from your tea by changing the temperature and time that you steep it for, although they don't say what we want, which is this is how much comes out. Changing the temperature changes this, changing the time changes this other thing. So let us stop there, because we have to plan and think about how we're going to actually do this. I would like you to think about this, because it is not obvious which way is better. Because very often we will be forced to do the less good version for practical reasons. Practically, this has the advantage that I only have to do it once, and I don't have so many errors. Practically, this other one has the advantage that the timing is a lot easier to fix, and I can afford more errors. I can stop this one better part way. This one you just have to do it all. So we will see. We'll have a think about how to do it and come back next time. So we'll leave it there because I've run out of time.